In this video, we will be going through the first topic of computer science for IGCSE and O levels. So, if you are with a similar background or you're wanting to join IGCSE or O levels, this is the video for you. Assalamu alaikum and welcome to my channel. We will be going through the computer science for IGCSE and O levels written by David Watson and Helen Williams. So, let's get into the video. I'll show you the main cover of the book so that when you want to download it, it's easier for you to identify the book. Also, the book is available online. I cannot link in the description because sometimes there's a copyright strike. So if you want me to show you how to download the book online, just comment and I'll make a separate video about it. Let's get straight into the topic and see what our first chapter says. The first topic is data representation, and the first section is computer systems, right? So computer systems, being the computer science and being the IGCSE O level student, we have these components in the computer systems section, which will be comprising of 6 different chapters basically. And in these different chapters we will go through some practical and theory approach. By practical approach, I mean that we will have to carry out some conversions, which we will see in our first topic. So let's get into the topic and see what we have. Data representation. First of all, I would really appreciate if you have any kind of notes with you so that you can note down the important things that I tell you about these topics, because I will be explaining the important questions from the exams point of view. That will be very helpful for you. Data representation is important in our computer systems or machines because anything that is visible on our screens that you can see is data. It can be a text, an audio, a video, or an image. Any such thing that is visible on our screens is considered as data. Hence, data representation is very important. In this data representation, we have certain mechanisms that are working to make things possible according to different machines. And these are known as number systems. Number systems are essential to measure something or to have an idea of a certain value. The most basic number system that we have, that we use generally, is the Denary number system that we are all familiar with, and it's the most common number system that is used in our daily lives. So that starts from 0, goes all the way up to any possible combination of values. Keeping that in mind, Denary has some multiples of 10. So you might remember the Denary system from junior grades when you started the place value and you started learning the multiples of 10. Keeping that concept in mind, we will move on to our first number system, which is the binary number system. The word binary stands for two possible values. It can be either 0 or 1. It can be either true or false. It can be either yes or no, or on and off. Any possible combination of only two values will be covered in binary number system. These number systems have base that is also known as a subscript. So a subscript or a base represents the total number of values that can be represented through a number system or in a number system. So for example, the base of binary number system is 2, which means that it can only represent with two values. It cannot have more than two values. It can only give two values, right? And those values will be 0 and 1. There's a very important question from the paper's point of view, that why do we need binary? We have other number systems as well. Then why do we need binary? And this will be included in your exam. Keep that in mind and note it down right now. Because our computer systems or machines consist of millions of tiny switches. And those tiny switches can only be in two possible states, that is on and off. Now, if we relate that to our 0 and 1, which is the range of possible values, that can be represented with binary, it is relatable. That's why, because of those switches, we need binary in our computer systems to represent data. Moving on, whenever you will have the question about these number systems, it will be in the form of a conversion. Why do we need to convert from one number system to the other number system? Why can't we stay in the same number system? Why can't we always use the binary number system? The answer is that we cannot understand zeros and ones. We don't know what these zeros and ones mean. That's why we need to convert the value, the original value, the original data into an understandable number system. In our case, that's Denary number system, right? So we will be going through these conversions in the practice examples as well as in your exam. So similar questions will be asked. We have first shown this table, as you can see on the screen, which actually compares how we can relate our binary number system to the Denary number system. It shows us the headings of 10, which are raised to the power. So any heading will be any value raised to the power. In the Denary number system, the base of Denary is 10. Denary, deca, see the relation? The base of Denary number system is 10. So we will always be using 10 in the headings. The first heading will always be starting with raised to the power 0, and then 1, 2, 3, 4, and so on. It keeps going. So if we want to relate this concept and implement it in our binary number system, the base of binary number system is 2, right? So instead of 10, we will have a 2, which will be raised to the power, right? So the first one will be 2 raised to the power 0. The second one is 2 raised to the power 1, 2, 3, 4, and so on until our number or the bit ends. And what is a bit? This single value is a bit, the one that is highlighted. This single value is a bit. This is a bit. Always start from the right side in the headings, go all the way to the left until you reach the last bit. You don't need to go beyond the last bit because there's no point of that. So start from the right, go all the way until the last bit. The first conversion that we have is from binary number system to the Denary number system, right? So we will have a value which will be in binary. We will have some bits. It could be 7, 8, 16, any number of bits, and it will be a combination of zeros and ones, obviously, because binary cannot have 2, binary cannot have 3. It will be either a 0 or a 1, and we will have to convert that whole combination into a Denary value. It's very interesting because once it is in Denary, we might be able to measure it. We might be able to have an idea because we cannot understand binary. The first value that we have is 1110, 1110. Let's solve this. So we have the value. Let me just quickly write the value. We have 1110, 1110. This is the binary value. The first thing that I need to do when I'm doing any conversion, general rules you can say for any conversion, whether it's a binary to Denary, Denary to binary, any possible conversion. First things first, I will write the headings, right? So the headings always start from the right side, go all the way to the last bit. Since it's a binary conversion, I will be using the base 2, 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3, 4, 5, 6, and 7. See, till the last bit. Now the next step, I just need to write the answer of these headings. So anything raised to the power 0 will always and always give us 1. Even if I have a million raised to the power 0, it will always give me 1. And 2 raised to the power 1 is 2, and then 4, 8, 16, 32, 64, and 128. If you want to know how we found out these values, anything raised to the power means multiply that by itself. 2 raised to the power 0 will always be 1. 2 raised to the power 1 is 2. 2 raised to the power 2 means multiply 2 by itself 2 times, right? And this becomes 4. 2 raised to the power 3 means multiply 2 by itself 3 times, that is equal to 8. 2 raised to the power 4 means multiply 2 by itself. Now you know the answer, which is 16. See, that's how I am finding the answer to these headings. Once I have all of these answers, I just need to multiply them with my bits. For this step, you can start from the right side or the left side. It doesn't matter. But the headings must start from the right side. I'm just going to start from the right side. So I'll take my heading, which is 1, and multiply with my bit, which is 0. And then I'll take my heading, which is 2, and multiply with my bit, which is 1. Then the next heading, 4 multiplied by 1. The next one, 8 multiplied by 1. The next one is 16 multiplied by 0. The next one is 32 multiplied by 1. 64 multiplied by 1. And 128 multiplied by 1. The last step is I just need to add all of these together. Add it here. All of these. Once you solve this, you will have your answer, which will be the conversion of this binary value into the Denary number system. Once you solve this, you will have the answer, which is 238, which is the Denary equivalent of the original binary bit. Hopefully, this conversion is now very clear and you will be able to perform any binary to Denary conversion. Keep in mind, these conversions require practice, just like mathematics, because there are going to be more conversions as well. There will be Denary to binary as well. There will be Denary to hexadecimal and hexadecimal to Denary, binary to hexadecimal. Don't get overwhelmed. Don't get confused. Just practice this first one, and once you get a hold of it, it will be easier for you to implement the same rules to the next conversions. Here's another example as well. I'm just going to quickly take you through this example. These are the bits, right? And what we did is we just wrote the headings, right, on these bits, and these bits go beyond 128, so we have more than 8 bits basically. So we just need to keep going until the last bit, and once we solve that by multiplying the headings with the bits, we get the answer, which is 1931. If you're enjoying the video so far, a sub to the channel would be helpful. That's it for this video. You need to practice these conversion by going through the examples and the activities, and I'll see you in the next one.